Chemical Engineering, Polymer Science 757, Palmen Rheology, HH Winter Lecture 10A. About 120 years ago, Boltzmann developed the concept which we are using here, the concept for describing the linear viscoelastic behavior of materials. The equation is very simple. I have them here in front of me. It contains a single material function, a single material parameter, so to say, and that's the relaxation modulus. So if you know the characteristics of the material in terms of this modulus, you can calculate all kinds of transient flows with that. And the advantage of this type of equation in shear, now we're just talking about one component, is that everything reduces to a scalar representation. The mathematics is very simple, and you don't need any training really, except for just maybe solving an integral or differential occasionally. So mathematics is simple, and you can go right ahead with that. That's one reason why it was very popular to describe materials easier early on, even for chemists, if I may say so, as compared to engineers or physicists who probably like to go deeper into mathematics. Now, this equation holds for materials in the equilibrium state. If you deform the material beyond the equilibrium state, different material, it has to be expected. So that's why we have to stay in the linear range. And today we will use that. Now, the person who is associated with that is Ludwig Boltzmann. Here, he was born 1844 in Vienna and was professor in Vienna and in some other places, Graz. And he's most famous for his development in thermodynamics. So the linear viscoelastic framework is just a byproduct. It's probably a minor accomplishment in his career, but it is quite an accomplishment. Later on in 1806, Boltzmann took his life. He got very depressed and had all kinds of problems. So one day he just, I guess, couldn't manage. And now look at the hairdo at those days. This might be due to lack of shaving equipment. But it looks fantastic. Maybe it will come up as a fashion. Next to him, by the way, I have a Scotsman here, Maxwell, who described the relaxation or the transient behavior of gas material, and he derived a simple equation which described viscoelastic properties of materials, the so-called Maxwell equation. We will use his single exponential relaxation modes for describing behavior. We call those the Maxwell modes following Maxwell. About the same time as Boltzmann proposed his linear viscoelastic model. So we will use this equation of Boltzmann in the following. And for the time being, we will assume that we know this material function from somewhere. Some friend gave it to us, and we are going to use it. I have to come back to this, of course, and we will have to discuss possibilities of measuring the relaxation function. But for the time being, we assume that we know this function in form of a continuous spectrum or in form of a discrete relaxation spectrum. And I will introduce those spectrums in our calculations. Now, having this function introduced here, we can choose all kinds of strain histories, all kinds of transient experiments, and calculate now the stress during startups or any experiment you would like to know in shear and in extension. And the result of those calculations would be material functions which are predicted in this case. They're not coming out of an experiment. The next step then will be the measurement of those material functions, and somehow the inversion of the measurements will give us the relaxation modulus. So we will pick just the material function which is easiest to measure at highest accuracy and which can be converted most easily into a relaxation modulus A single experiment of that type will give us the modulus, and then from that on we can predict all other material functions. There's a relation between material functions which has been developed and described in books of Ferry, for instance, those interrelations. Staverman, Schögel in the 40s and 50s developed those relations for linear viscoelastic functions. We should come back and explore the range of validity of those material functions and of the Boltzmann equation in general. So the determination of the functions will be covered next time, but I would like to cover everything else today if we can manage to proceed fast enough. Now, the first example I would like to propose here is the steady shear viscosity. We would say a material is covered with the Boltzmann equation, like here, and we will choose now a certain kinematics, and that's the kinematics of steady shear flow. In a real experiment, you would put your sample in the rheometer and then turn on the shear flow and keep the shear rate constant from now on. So this would be the prescribed history. And as a response, the stress will be growing, growing, growing. And after about 5 times the longest relaxation time, the stress will not change anymore. You reach steady state. If you keep going from here on, the material does not remember the startup situation. So for our modeling calculation, where we are after the stress in steady shear flow, so for these modeling calculations, we can assume that the material has been exposed to constant shear rate forever. During its entire past, it always was exposed to steady shear flow. So in this integral up here, from minus infinity to the current time t, we put in a constant shear rate, and we'll get a reasonable stress, neglecting the startup situation. So this is our hypothetical shear history, which we will be using. And in our model here, the stress, the shear stress, is given by a constant shear rate over the entire shear history. We can put the constant outside and integrate the modulus to get the viscosity. You will realize that we have the stress then equal to the shear rate times a new term, and this new term is the steady shear viscosity. As we defined it before, that's the material function. So the viscosity is the ratio of shear stress versus shear rate, eta 0, because we are operating at low rates, talking about the 0 shear viscosity, and that's given as the integral over the modulus from 0 to infinity. It's quite interesting to note that viscosity, which is associated with loss phenomena, is described with the relaxation modulus here. And this modulus, initially, we probably associated more with elasticity of the material. But it describes the relaxation behavior. And during a steady shear flow, you're constantly building up stress, and the stress is relaxing at all times. And that's why in a steady state, all the energy is dissipated all the time, and that's expressed in this steady shear viscosity. This 0 shear rate viscosity now can be expressed in terms of the relaxation modulus. And we assumed for the time being that we know the relaxation modulus in its continuous form. Let me go back to a slide of the last class. We said the relaxation modulus is a decaying function in time, something like this. And for the liquid, it would go down to 0. And we can describe the relaxation modulus as a sum of Maxwell models. A single Maxwell model would be just an exponential decay like this. We could describe it as a discrete model like this, or as a continuous spectrum of those Maxwell modes. See, if we take an infinite number of Maxwell modes as written down here, actually we only have a finite number in real discrete models. So if we take an infinite number, this model converts into this continuous model. So they are really on an equal footing, those two. I will use now the discrete representation and the continuous representation when calculating material functions. In this case, calculating the shear rate, the exercise for calculating the steady shear viscosity. So we replace this by the continuous spectrum. This is the continuous spectrum. And integrate, but first we would change the order of integration. See, ds, we would do this at the end, this integration, and integrate over the entire spectrum initially. So if we take this part here and integrate the exponential function, put in the limits, then you will realize that this is equal to 1, and the zero shear viscosity is really the integral over the main part of the kernel here in our continuous spectrum, h of lambda d lambda, integrated from 0 to infinity. And the modulus up here, remember, was h of lambda times this exponential term and then d lambda over lambda. So this this is g of s, and this is now the viscosity. For the discrete spectrum, we would calculate the steady shear viscosity by putting in this finite number of Maxwell modes, integrate this. Every exponential function can be integrated very nicely, and you get the viscosity as just the sum of gi lambda i's over all n terms. So that's the zero shear viscosity in a discrete representation. Now we know the value after long times. Let's look at the startup itself, which we neglected in the beginning. So we really would like to know what's happening at inception of a shear rate which is constant. So turning on the machine, shear rate is constant, and this is prescribed. The response of the material with respect to the shear component. I'm just limiting myself to the shearing. The shear component is given again here as in form of the Boltzmann equation, and we would have to put in now the specific history. Gamma dot is 0 in this first part, and it's constant and a finite value in the second part. So let's break this integral into two parts, so minus infinity to 0, where the shear rate is 0, plus the part where the shear rate is constant from 0 to t. Now, this constant value can be put outside. We integrate as before, and we find that the shear stress is given as the shear rate times the integral over the relaxation modulus. And this is now integrated from 0 to t. If you would integrate this up to infinity, again, you would get the steady value which we calculated before. That's the general formulation for the relaxation modulus, but we know the spectrum, or we assume we know the spectrum. So let's put in the continuous spectrum first, where, again, this is the continuous spectrum integrated here from 0 to t. In the startup mode, we change the order of integration, integrate the second part, and we find a exponential decay function in this. At long time, the second term will drop out. We will get steady conditions. I didn't evaluate this further. We will learn about h of lambda for specific materials. And when you have this h of lambda, you can proceed from here. But that's as far as we can go in the moment. For the discrete spectrum, the sum of Maxwell modes is introduced into the integral from 0 to t, and simple integration will lead this function. And that's quite nice here. This is the fun factor, is the steady shear viscosity, and it's multiplied with those exponential decays. The longest time will need the longest startup time. Or in some cases, when we talk about, for instance, material of very high molecular weight, then this longest relaxation time diverges to infinity. And then our startup time is infinitely long. And that's captured in this type of relaxation spectrum. So we can quantify the startup experiments. When we look at materials at the gel point, for instance, we have a divergence of the longest relaxation time. At the gel point, the molecular weight goes to infinity, and the longest relaxation time diverges, goes to infinity. And the material will never reach steady state. And you can see this from this modeling. So you cannot produce steady shear flow in a material near the gel point. Another modeling, another material function which I would like to model here is step strain. A strain of value gamma 0 is introduced into the material. In a real experiment, there's a finite rise time, t0, for introducing the strain, maybe 500 milliseconds or so, 0.5 seconds in a real experiment. But that's a finite time to introduce the strain, and we can assume that during that time, maybe the rate of deformation is constant for our modeling. Just doesn't matter so much what type of kinematics. So let's say the strain increases linearly here, and then it stays constant from there on. So the ideal shear flow history would be zero shear rate in the first part, constant shear rate in this part, so that after T0, the total strain is introduced. So the shear rate is equal to the total strain divided by the rise time. This is the approximation of the shear history which we are going to use. And beyond that, the shear history, again, is 0. We introduce that into the Boltzmann equation, find a 0 kernel in the first region from minus infinity to 0, find a finite kernel where the shear rate is constant during the short rise time from 0 to T0, and then have a 0 kernel again at this later time. Now, we can integrate this way. We put this outside here in, we put the constant shear rate outside, and then we take the limit where we say the rise time is very, very short in our real experiment for our modeling calculation, which is realistic. It's short compared to the relaxation times of the material. So we would take our model now in the limit of 0 rise time. The constant is out front, and we would evaluate this now for 0 rise time. Now look at this. If the relaxation modulus is evaluated at t prime equals 0, this would be g of t. And if it's evaluated at t minus t0, and t0 is about 0 itself, then it would be evaluated at g of t and in the upper limit. So during the entire integration, g of t doesn't really change. It's constant, and we can move this outside the integral and just call it g of t, and then integrate this integral, and it's just equal to t0. So in the limit of small rise times, where we would say in that short time, the modulus doesn't change because that time is so much shorter than all the relaxation modes we are going to look at, then this function is constant, and this T0 cancels with that T0, and we find that the shear stress is given by the shear strain times the relaxation modulus, and that's really the result we were looking for. Remember, that was the material function we discussed in the beginning, that we had the specific experiment in mind where material is put between two plates, and its shear deformation is imposed on the material. We measure the stress response, and that was given by the relaxation modulus. And we use that, for instance, for deriving Boltzmann's equation in a simple fashion, in a phenomenological fashion. So that's the relaxation modulus, which we should be able to calculate with our modeling. Let's calculate the same modulus different way. I would like to get used, those are exercises, I would like you to get used to this type of linear viscoelastic modeling. So in the second case, we use an alternative form for the Boltzmann equation, where we say the stress is given by the memory function times the strain between t prime and t and then we integrate this kernel from minus infinity to the current time t. Remember, that was an alternative formulation of the Boltzmann equation where the strain was written here instead of the rate of strain. And here the memory function is minus the derivative of the relaxation modulus. So it's not a new, it's not a new material function. If we know g of t, we also know the memory function. Now, for our modeling here, we have to know the strain history at the two regions from minus infinity to current time t. This is the first part. and there the strain between this initial part to the current time t is equal to gamma. And then we have in the second period, where t prime is larger than 0, we have a 0 strain. And that goes something like this. Let me come back to the experiment. The experiment said that we put in maybe a tangent alpha in. We were shearing a little material element from an initial shape to some final shape, and this would be this part here would be alpha, which describes the shear angle. So this is then really gamma, which we introduce in the experiment. This is the experiment as a function of t. Now we would like to know, for instance, the strain from some time t prime here to the current time t. And this strain is given as an integral over the strain rate during that period, dt double prime from t prime to t. And you realize that between t prime and t, there's no shearing motion, so the total strain between t prime and t is equal to 0. But the strain from some time over here, time t prime in this case, let's talk about this other case here, t prime in the past, the total strain between here, where the material element had this shape, to the strain where at time t, where the material element has this shape, is equal to gamma 0 to the total deformation. Okay, so in the first period, we have to put in a gamma. The first period, we have to put in a gamma 0 for the strain. This is from minus infinity to the current time. Excuse me, from minus infinity to 0. And then for the second period, from 0 to t, there's no further strain, so this is equal to 0. And this part drops out. We integrate this simply and find that the integral of this here is given as minus the modulus g of t, I should have put here, or g of s as a function here, t. And then evaluated between t and infinity. At infinity, all the relaxation is over, so the modulus is equal to 0. The stress has decayed to 0, so the modulus is 0 at long times, and this is the modulus at time t. And the result, again, is shear stress given by the modulus times the shear strain. I'm using a substitution here, and I forgot to mention this, and maybe I should come back to the startup example when looking at startup of shear flow. For instance, this type of integral here, where t minus t prime can be used as a new variable. I'm using this all the time. So s would be a new variable equal to t minus t prime, and ds is minus dt prime in this case. And the lower bound of the integral, t prime is equal to 0, so you put in 0 here and see s is equal to t at the lower bound. And the upper bound, t prime is equal to t, you introduce this here, and you find that s is equal to 0 in this case. So you have, for this one, you have minus ts. At the lower bound, you got t, and at the upper bound, you get 0. And the minus sign here is used to interchange the order of that integral, and then you have an integral from 0 to t ds, and then written in the ds kernel. So please go through an exercise like that so that you can that you appreciate that approach. The next material function I would like to calculate is most important for determining the relaxation spectrum. And actually, we will use that type of experiment later on. I will come back to this. So it's good to have the fundamentals. More than, maybe 150 years ago or so, the electrical engineers analyzed the behavior of dielectric media when exposed to alternating currents or alternating fields. And all the framework which they developed in the last century has been transferred to rheology, where we expose a material to a periodic deformation, and then measure or observe the response to that periodic deformation. In this case, we would expose the material to small amplitude oscillatory shear. Small amplitude oscillatory shear. The shear strain is a sinusoidal function versus time. Now here I didn't plot time by itself. I plotted omega times t, since we're talking about an experiment at constant frequency. You can choose this as high frequency or low frequency, but we would like to do this at constant frequency. As a consequence of this strain here, we have a strain rate, just being the derivative of this function here, which is just a cosine function. So it's described here as, again, same periodic function, but shifted by 90 degrees. Okay? The strain rate is 90 degrees out of phase with the strain. The stress response now, marked here with this red line, is somewhere in between the strain and the strain rate in its, let's say, in its phase shift. If you introduce a perfectly Hookean material, perfectly elastic material, then the stress is in phase with the strain. And if you put in a perfectly Newtonian material, then the stress, this red curve, is 90 degrees out of phase or exactly in phase with the rate of deformation tensor. And for viscoelastic material, there will be a phase shift delta, and we will have to analyze this delta. It depends really. That's one of the characteristic quantity which we have to measure. It depends on frequency, for instance, and changes from material to material. The amplitude is also material dependent, so the response is characterized by the amplitude and by the phase shift. So let's model this type of experiment in terms of the Boltzmann equation. The strain rate is given by the front factor. It's omega times the amplitude. And the periodicity is given by the cosine function, omega t prime. The relaxation modulus we assume to know for the time being. Later on, we will measure the response and then determine the relaxation modulus. So let's carry this along and just leave it as it is. The front factor here can be moved outside. So this is our characteristic strain rate, omega times the amplitude of the experiment. And this cosine function can be rearranged. As a first step, again, we introduce S is equal to t minus t prime. That's really the distance from the current time into to the time in the past, to some event in the past where a deformation has taken place. So we will write down g of S, and this t prime is equal to t minus S. And the bigger S, the further you look into the past of this experiment. So we change the variables here. It goes now from 0, from the current time, into the past, to really into the infinite past, infinitely far backward. And this cosine function can be replaced using trigonometric relations into a product of cosine omega t cosine sine omega s, here taking those products, plus sine omega t sine omega s. And we can rewrite now these integrals and note that we are integrating over ds, so omega t can be put outside. Okay? So we have omega times the, let's start with a sine contribution, g of s times sine omega s ds times gamma 0 times sine omega t. And remember, this was the strain. This is the input. This is the prescribed strain, periodic strain of our experiment. Plus a function, again here, which contains s, the integral over s from 0 to infinity. And here we take the cosine contribution times gamma 0 times cosine omega t. Now, this whole front factor is called the storage modulus of the material. This is called G of prime, and the second part is called G double prime. This is the loss modulus of the material. The ratio of the two is the phase angle. That's the shifting of the stress. Yeah, remember, we would like to know now, having the calculation done, we would like to know how big is delta, the shift, as compared to the strain. Strain goes with sine omega t, and there's a shifting delta. And this delta is given by this relation, tan delta is G double prime over G prime. And I would like to prove that to you. So let's write down the stress as an amplitude times the sinusoidal function shifted by delta. It has the same frequency as the input frequency. That's the requirement for a linear response. If this omega would be different, you would get some maybe higher order harmonics, and you would operate outside the linear range. So within linear range, the response has the same frequency as before, but shifted, now phase shift. We can decompose this now again into a function which goes with a strain, sine omega t, and a function which goes with a strain rate, cosine omega t. And the front factor here is really G prime over the amplitude, and this front factor is G double prime divided by the amplitude. And if we rearrange these expressions, here we get G prime expressed with cosine delta, G double prime with sine delta, and the ratio, we take the ratio of the two and find tan delta, and that's the phase shift. So that's what I wanted to show. Tan delta is used quite frequently as a material function. If you have G prime and G double prime, then you can calculate tan delta. Or if you have maybe G prime plus tan delta, you can get G double prime. Well, you need two material functions to describe the behavior. And these material functions, for instance, are summed up here for the Boltzmann equation. In dynamic mechanical experiments, you find that the modulus describes G prime and the modulus describes G double prime. So one material function is sufficient to describe the storage part and the loss part. Okay? It's not that this is the elastic contribution and this is the viscous contribution of the material. Let's go a little further in this concept. And somewhere down in your handouts, I wrote down the Cox-Merz relation. But let's talk about this here. It goes something like this. We can invert the equations which you saw before and express now G of t. Remember, these were our equations. We put this outside this G of t by applying a Fourier transform from 0 to infinity. And then we find the relaxation modulus in terms of G prime, and we find the relaxation modulus in terms of G double prime. So now, if you know G prime, you have all the information to get the relaxation modulus. Or if you need G double prime, somehow they are intensely correlated. And one group which recognized that was the group around Cox-Merz, who wrote this Cox-Merz relation. You know, you can equate those and rearrange everything, and you find now a relation between G prime and G double prime. So if you have G double prime over the entire frequency range from 0 to infinity, you can convert this into G prime and vice versa. Very famous relation which you need to, well, let's say when you do experiments, your data have to satisfy this Cox-Merz relation. Otherwise, something is wrong with the experiment. And it's very easy to get artifacts in an experiment. So you can use that to check whether your experiment is okay. Now, having defined G prime and G double prime, we can move again further by assuming we know the relaxation modulus in terms of a continuous or discrete spectrum. Let's see how this looks like. We define the relaxation modulus, introduce the continuous spectrum, interchange the order of integration, and then integrate over over time, yes, and then we get all the frequency part comes out here. The frequency is in here and frequency is out there. So if we integrate this frequency part, we get this type of coefficient, and we introduce this into the kernel, and then have to integrate a second time. So this gives us G prime of omega. Note this type of group. This occurs quite often. Omega lambda square over 1 plus omega lambda square. This group for the storage modulus. And if you go through the same procedure for G double prime, you get a coefficient here, which is omega lambda, and this divided by 1 plus omega lambda square. And you have the two relations which describe the response to a dynamic mechanical experiment in case of a continuous spectrum. If you do the exactly the same derivation now for a discrete spectrum, you find these solutions here, the fun factors, GIs, and then the lambda i's of the Maxwell modes. We're putting in a sum of n Maxwell modes and calculate G prime, G double prime, and we find this relation. A typical experiment for the material in small amplitude shear is giving us G prime, G double prime of this type. If you please change the size a little bit, Becky. Yeah. At low frequencies, G prime is attempting a slope of 2. And if you have that, then you know that it will continue with that slope to even further frequencies. So this is all the information you need on this part of the spectrum. It's the so-called terminal zone, and you're all set. If this is a slope of 2, and this is a slope of 1 for G double prime. At higher frequencies, this is the region where, for instance, this bouncing putty would be flowing on that time scale. Okay? At shorter times, or intermediate times, the material behaves rubbery, and G prime levels off to a plateau type, and this often is called the rubber plateau, or it's called the plateau modulus. And then beyond that, glassy behavior, at shorter times, higher frequencies, the modulus is going up. So that would be a typical fingerprint of the material as it comes from a rheometer experiment. And when we talk about determining spectra, we have to look at this type of experimental data set and convert that into h of lambda and into Maxwell modes. And that's a fairly straightforward procedure by now. It's quite complicated, but it's a solved problem. For us, I think it's a solved problem. Yeah. You can go into all kinds of details. Yes, question? Yes. When talking today about the material functions, I also will come back to those shift factors. BT is a shift factor up and down. It's given by rho t over rho 0 T0. I never remember, I have to check which one is on top and which one is on the bottom, but I think this is BT. And then omega t is given by Arrhenius relation or WLF or Vogel relation. So we will come back to this. We will use the linear viscoelastic approach and see what time temperature superposition requires, or what's the consequences of that observation. So I will come back to this in actually just shortly. But before that, let's look at the terminal zone again. Remember the slope of 1 and 2, and we should see that in our modeling. So let's take the limit of G prime as the frequency goes to 0. This was our solution for the continuous spectrum. Now, if omega goes to 0, then under the bracket, 1 will be much bigger than this part here. And the omegas, we have omega squared, lambda squared on top divided by 1. And omega squared will go outside in all the functions with lambda. You have lambda squared over lambda, so 1 lambda will be canceling. And that's proportional to omega squared. And that's indeed the experimental observation at very low frequencies. And that's all, all you can see if you go to lower and lower and lower frequencies. So no more information beyond the terminal zone. And that's very nice. At high frequency, we are in trouble. We always could go to higher frequencies, shorter modes, and would see further and further and further details of the molecular motion at smaller scales. At the loss modulus, if omega goes to 0, then this function reduces to omega lambda over 1 here in the limit of omega going to 0. And this lambda cancels with this one. Omega goes up front, and the loss modulus in that limit is just omega times this function. And remember, that was equal to the 0 shear viscosity. So in the limit, if you just take G double prime to, if you just take this slope here, then you get the 0 shear viscosity without any new experiments. That's a nice thing when intercorrelating the functions, the material functions of linear viscoelasticity. One experiment can be intercorrelated with the other experiment very, very nicely. So we do a dynamic mechanical experiment and extract steady shear viscosity values at low rates in this case. So that's the limit. There are many different ways people like to describe their data. So let's quickly list a few alternative ways of doing it. It's no new information, as you will see quickly. For instance, the complex representation is popular, where one defines a complex modulus in terms of a storage modulus plus I times the loss modulus. So this would be a complex number. This is the real part. This is the imaginary part. And you could express now G prime, G double prime in the integral with the sine function and the cosine function as we had before. And this function here, the sine omega t plus I cosine omega t, is equal to, in complex notation, is equal to I times e to the minus I omega t. So that's a shorthand notation. So you could say the complex modulus is just I omega, you combine this up front, times the modulus times e to the minus I omega t. You will see this in the literature. No new information. It's exactly the same. It's the same way of describing things. For the continuous spectrum, you would introduce now this notation, and you express the complex modulus in terms of this function, and then you have I omega here, I omega. This front factor contracts with the exponential function, and for the discrete spectrum, you get a similar function. This is a nice exercise which you could go through on your own. It wouldn't be any new information. Now, the second alternative representation, which is really quite popular, we plot this along with G prime, G double prime, is here in terms of the complex viscosity, where we would say eta star is equal to eta prime minus I eta double prime. Now, eta prime is equal to the loss modulus, G double prime. So you change the prime into double prime over omega, and you have the conventional definition. And eta double prime is G prime over omega, and you have this with a sine function. And the relation between the complex modulus and the complex viscosity is just here with the factor I omega as described down here. No new information. If you have G prime, G double prime, you can calculate the other material functions freely. Let's have a short break here and then continue look at other models, some other functions. 1057, Polymer Rheology, H.H. Winter, Lecture 10b. In the experiment which I just discussed in the dynamic mechanical experiment, the material is exposed to a periodic deformation. And in a real experiment, you really start from rest. The material is at zero strain for a long time, and then you start your machine. And we would like to know how long is the startup? How many periods do you have to go with a strain until the stress response doesn't memorize the startup? So that would be an interesting calculation for your interesting exercise. You would use the Boltzmann equation, where in the first part of the integral, the rate of deformation is 0, and then from 0 to t, you start deforming the material in this type of fashion. And then actually, if this should be cosine omega t, if this is the cosine omega t prime, since we're talking about the rate of deformation in this case. The result of that is between 1 or 2 periods are needed until steady state is reached, independent of the longest relaxation time. So the startup of this experiment is different from the startup in the steady shear flow experiment. Steady shear flow, you probe all relaxation modes of the material, and the longest relaxation time determines your startup time. In this case, the experiment only probes the relaxation times in the order of a period of your material. So omega t equals to about 2 pi. In that order of magnitude, those relaxation modes are probed, and they determine the startup time of your experiments. And that's a key feature for the whole experiment using dynamic mechanical experiments. Okay? Now, we could do some modeling calculations in creep also, but I don't want to go through those through the details. So you have something on this in your handout. Impose a certain stress and then look at the strain response. The difficulty in the modeling of those creep experiments is the following. If you prescribe the stress and calculate the strain rate, then you have to invert this integral to get the solution. And that's sometimes complicated. But for linear viscoelastic equations and for simple creep experiments, you can do that interconversion with Laplace transforms. And talk somebody in control theory, they do the same thing when analyzing their systems. Or somebody in electrical engineering has all the equations available in the textbooks. Now let's talk about time-temperature superposition. It had been realized by Tobolsky, Ferry, and Staverman, and people in the late 40s, that the response of the material as a function of temperature, here this is the relaxation modulus in the Gleissle regime, glass transition, rubbery regime, and flow regime, that this response is very, very similar to the response versus time. This is the relaxation modulus now plotted at at long times. No, I was right. At short times where the material behaves glassy. It doesn't have time to rearrange. It's a dynamically induced glass transition. Then at longer times, transition to broader ranges of relaxation, and then rubbery behavior at this time scale, and then the flow regime at very, very long times. And this goes down to 0, and the cutoff here, really the longest relaxation time, determines the terminal zone of the spectrum in G prime, G double prime. Okay, so 1 over omega in the terminal zone of G prime, G double prime is associated with the cutoff here of the relaxation modulus. Here is associated with that time. Now, the real experiment has not been done over so many decades. The real experiment was done over 2 or 2.5 decades, and then with time-temperature superposition, the fingerprint was achieved over so many decades. Now, this time-temperature superposition requires a certain behavior for our a certain behavior of our relaxation time spectrum. So let's look at the relaxation time spectrum, which, remember, was defined by the relaxation modulus. Relaxation modulus is given by the relaxation spectrum, and h of lambda would be some function, something like this. And we can represent this as a continuous function, like in the plot, or we can represent it in a discrete mode as a set of Maxwell modes. G of t is given as those Maxwell modes are. H of lambda is just given in discrete fashion. Now, this representation of the discrete modes, and that's important to note, is completely equivalent to the continuous representation as long as we pick enough modes. So if n goes to infinity, then this converts into that representation. And we can use now the discrete representation to push our arguments a little bit further. And with that spectrum now, I would like to go back to time temperature superposition. We will introduce that discrete spectrum into the Boltzmann equation and maybe calculate material functions G prime, G double prime, G of t as we did before at two different temperatures and see how we can shift those into each other. And you will realize that the relaxation modulus, for instance, calculated at one temperature or measured at one temperature here is described in this fashion with a discrete representation, set of n Maxwell modes. And at some other temperature T0, it will look exactly the same. However, GIs are evaluated at temperature T0, and the lambda i's are evaluated at T0. So the temperature will affect the material parameters in our equation. And here comes the postulate for the time temperature superposition. It says that all modes, GIs, lambda i's, all GIs and lambdas, are shifted in the same way. All Maxwell modes are shifted in the same way. The front factor, G of t, is given by the front factor at temperature T0, at the other temperature, multiplied with the shift factor. And this was this BT, which we saw before in the G prime, G double prime formulation. And the relaxation time at time t is given by the corresponding relaxation time at temperature T0 times the shift factor between t and T0. And this shift factor is known to be, we can get this from experiments, it's known to be an Arrhenius relation. It's a straight line. If you plot it as 1 over t here at log, it's just an exponential function here. Or over wider temperature ranges, very often it's non-linear, and especially at lower temperatures. At high temperatures, it becomes linear. At lower temperatures, note I'm plotting 1 over t, so low temperatures are out here. So at low temperatures, it has curvature, and it will be described by WLF, Williams-Lendl, and Ferry equation, which was published in 1956 or 58 or something like that. And you can read about this in Ferry's book very nicely, or by the Vogel equation, which captures the same temperature dependence for some other reasons. And typical values are given here for polyethylene and polystyrene, so you can do your own calculations. Okay, now let's come back to the discrete spectrum. We introduced the discrete modulus, discrete moduli, as described before. So this is the modulus at temperature T, and the front factor at temperature T we replace by the front factor at T0 times this coefficient, which is a constant. We will pull this forward. And the relaxation times at temperature T0 have to be multiplied with a shift factor. We can rearrange this by, we pull this forward and then divide everything. So we put this over on the other side. So this would be 1 over BT. And the time is scaled now at T 1 over AT. And the universal plot, now independent of temperature, would require this type of modulus scaled with the density and the temperature, and this type of time where the time is scaled with a shift factor at the current temperature. Now, if we would look at this curve at reference temperature T0, then the shift factor would be equal to 1, and this coefficient would be equal to 1. So if we take this curve at the reference temperature level T0 as it is, then we can predict the modulus at some other temperature T by just multiplying here by using those reduced variables. And that's the procedure described in the literature. So we are using reduced variables. We're using for the modulus multiplied with BT and the time divided by AT, and then for G prime, G double prime also having the same coefficient, but omega has to be multiplied now with AT, and for the viscosity we have this front factor, and also AT is coming in with the viscosity, and this gamma dot AT. Now you could calculate this by taking a discrete spectrum, determining eta 0, the zero shear viscosity, which is given as a product of GIs, lambda i's, summed over all in Maxwell modes, and from that discrete representation you get exactly the shifting with respect to omega, and then with the shear rate you have to when you look at startup of shear flow, you get exactly that shearing. We're talking about linear viscoelastic behavior. Now, what are the limitations of the behavior which we are talking about here? What can we do with the Boltzmann equation? Well, there are several limitations. First, the material has to be in an equilibrium state. So the deformation only can be very small. And the question is, how small is small? I mean, somebody puts a material on your desk, and you want to predict now startups of shear. What strain would you take? You could take bets now. Is it a strain of 1, or is it a strain of 20 or so? Now, for polymer melts, that characteristic strain is in the order of 0.1. That's a characteristic value. For suspensions, the characteristic strain is about 0.001. So it's a very, very small strain. If you deform your material beyond that, it becomes nonlinear, and you get all kinds of phenomena. So the first criterion we have to look at, the question is, how small is small? I'll keep this slide. I will look at the other limitations in a moment. So how small is small? It's impossible to predict. If you would have, you could take a molecular dynamics model, maybe Doyle-Edwards model, which applies to large strains, and then quantify the limitation and see how small do you have to stay to have no influence of strain on your data. But for an experimentalist, it's very easy. We just measure G prime at a constant frequency at increasing amplitudes, and at low amplitudes, it's a constant value. And if we go to larger and larger strains, then it somehow deviates, and so there's a characteristic strain which is the maximum value, and this would be the material characteristic, say 0.1 for polyethylene. Now, for shear flow, we would say if we deform the material at very low rates of deformation, the material relaxes so quickly during the deformation that it's always in its equilibrium conformation. Okay? Very low deformations, always equilibrium. But if we deform the material beyond this, then the deformation is large, and we could introduce a criterion now. We could say that if the total strain which the material memorizes, and the total strain which the material memorizes would be our shear rate, which we were picking, times the longest relaxation time of the material. That's the biggest memorized strain. And if that is below the critical strain, which we determined before, then we are safe. Then we are in the linear viscoelastic range. And if this range, this is bigger, then the memorized strain is beyond toleration, and you have a response which is looking at an altered material. You see shear thinning, and this is how this longest, how the breakpoint in the viscosity curve is related to the longest relaxation time, you need the characteristic strain, you need that strain level to go in between. Remember when we talked about material functions, I mentioned that, and here I'm coming back to exactly this argument. Now, the second limitation which we are looking at is given by continuum mechanics. Remember, when deriving the Boltzmann equation, we linearized the strain tensor. We just added the strains. We said strain 1 plus strain 2 is giving us the total strain. But when looking at finite strain tensors, you know that this is not permitted. You have to multiply the deformation gradient and calculate a sequence of strain in a more complicated fashion. So you're really violating continuum mechanics when doing this. So I want to show this to you in two examples. We are looking at continuum mechanics now. If the magnitude of the strain, see, I'm taking a Cauchy strain tensor here, which is really 1 at small strains. So if this magnitude minus 1, if that's very, very small, close to 0, or very small compared to 1, then we are in the linear viscoelastic region. We don't violate continuum mechanics. In a sequence of 2 shear strains, for instance, we could say total strain of gamma, which we want to model as a sum of gamma 1 plus gamma 2. We would calculate a Cauchy strain tensor, which has the components as described here. These are the off components for calculating the shear stress. That's okay. We can really add everything. That's fairly simple. Only the normal stresses will be in trouble because this term is certainly not equal to gamma 1 plus gamma 2. There's some intermediate terms coming in. So normal stresses require a full description of the strain tensor, and I will come back to that later on when we introduce the full strain tensor. So I'm staying away from the normal stresses in the moment, just calculating shear stresses because of exactly this reason, because of this limitation. We cannot describe the square terms in the strain tensor. Okay? And the finger strain tensor has the same limitations. So it has a square term here and a linear term in the stress, and has a 1 down here. So same limitations. And now let's look at the extensional deformation. Let's assume we are stretching a fiber at a constant extension rate, epsilon dot. And the rate of deformation tensor is given by this type of strain tensor. Continuity requires that the sum of all the diagonal terms is equal to 0. The total strain which we would put in between some time in the past and the current time t would be just the integral over the strain rate. And the sequence of 2 strains then would be just giving us the first strain plus the second strain. If we use this addition type procedure which we used for deriving the linear equation with the relaxation modulus, for deriving Boltzmann's equation. Now, we defined a linear strain measure where we said the strain is just an integral. Instead of having just a component, I would say the strain now is equal to the integral over the strain rate from some time t prime to the current time t. And this is the type of thing we would like to evaluate. And we would like to evaluate the first term, say, on the equivalent to 2 epsilon dot in the rate of deformation tensor. We would like to calculate now. We integrate this equation here. We get E11 equal to the integral of 2 epsilon dot integrated from t prime to t. And this is just 2 times the first strain we put in the material. We're stretching our fiber a first instant, and then we're stretching it a second instant. And then this would be plus now the second strain in that linear superposition. Let's see how far we get, how much we are violating when describing everything in a linear fashion. Remember that epsilon, this epsilon is just equal to the log of the stretch. This is the log of the first stretch times 2 with this front factor, plus 2 times now the log, here this is 2 times the log of the stretch of the second stretch. L1 and L2 are the 2 stretches we are talking about. So we have now E11, as the square 2. We used, this is squaring L1 squared, and this is log of L2 squared. We're putting the 2 in. So when we combine those two logs, and then we have just log as the square of the first stretch times the square of the second stretch. Okay, so far our first component calculated in this linear fashion. And we could now take the exponential function, e to the e11, and we can, well, with our e11 is just, e to the e11 is just the square of L1 times L2 here. And we can expand now this exponential series in a linear fashion, 1 plus e11 plus 1/2 e11 squared plus 1/6 and all of this. And in the limit now of small strain, remember I was looking at the limit here where the strain, this is close to 1, or this minus 1 is equal, is very small. So in the limit of this being very, very small, then the square terms are dropping out, and we can use the linear relation. So we have to do something about the strain tensor to expand the linear picture to large deformations. And we can fix that very easily. We can replace the strain tensor with the finger strain tensor, and we can replace the strain weight tensor with the derivative of the finger strain tensor. And it turns out that exactly that equation is the large rubber-like liquid. It's an equation which Large proposed in terms of a network theory in 1956. So he used exactly this modulus, and then he used the right strain tensors. And then we are already, overcame that problem of the linear strain measure versus the nonlinear strain measure. And by putting in the right strain tensor, we can calculate the square terms. We can calculate the first normal stress difference in a linear viscoelastic experiment. And we can do that in shear and extension and describe all of this. And we will do that. So this will be one expansion, one generalization of Boltzmann's equation, which is worthwhile to discuss. That's very easy to overcome this problem. Now there's one more limitations which I wanted to discuss, completely different type of limitation, and that comes from the experiment. I already mentioned that limitation. It is given by the truncation of the spectrum. Remember, the data are not known at very short times. The modulus is not known at shorter and shorter times. Well, at higher and higher temperatures over here at shorter and shorter times. So there's a limitation. The same thing with G prime, G double prime at high frequencies. We don't know the data. But there's no limitation at low frequency because we are able to cover the material at the limit of long relaxations. So far about the limitations. Oh, here I even have a picture of the truncation. Yeah, that's what I mean. The data are truncated at high frequency when we take G prime, G double prime data. And this means that our relaxation modulus, which we determine from the data, we take the data, determine the spectrum, that those data are truncated somewhere in this range, and we don't know what's really happening. And this will affect our modeling. There's no problem at the low frequency since the spectrum will be truncated at the longest relaxation time. This will be just cut off here by a physically meaningful relaxation time, by a characteristic time, and will be important to determine this longest relaxation time from our data. This will be one objective. While we talk about dynamic mechanical data in spectra, there are a few interesting correlations which have been discussed in the literature. You will find them, you will use them maybe yourself. For instance, if you have h of lambda, if you have the spectrum, or if you have g of t, if you have one linear viscoelastic function, you can determine all the other functions. All the functions in Ferri's book you can calculate, you can determine if you have one spectrum. And this intercorrelation between material functions is very powerful, has been discussed extensively. So some people prefer creep experiments, and they prefer determining the relaxation spectrum or the retardation spectrum in that creep experiment. That's fine. They just get the spectrum there, and then they calculate the relaxation times from that, and just go back and forth at leisure. I will come back to this later on. We will determine the relaxation spectrum and then determine the spectrum in creep experiments. And it's coming out as a windfall. No further work is needed to do that. So Ferry, Tobolsky, Staverman, and those people looked at this in great deal. There are also empirical correlations. Up here, those are really exact correlations. You can go from one to the other by just mathematical manipulation. But then there are correlations which are found by just by people working with those data. We say, oh, there's something interesting, and if we have this information, we automatically draw other information. I will discuss one relation, small strain, which is quite interesting. Another one is as a set of relation between small strain experiments and large strain experiments. Linear viscoelastic experiments are really limited to equilibrium morphologies, equilibrium structure of the material. And there are some relations for expanding data in equilibrium to large strain behavior where the material is at completely different conformation. It's pushed out of equilibrium. And those correlations are quite interesting, and surprisingly they work pretty well. Now, the first relation which I found interesting to worthwhile here to mention is involving the slope of G prime, G double prime. Now, if you take the complex modulus, remember G prime plus I, G double prime, if you take the magnitude of that complex modulus as a function of frequency and take the slope of that in a log-log plot, then that local slope is proportional to the phase angle multiplied with 2 over pi. And that works amazingly well. Maybe it's related to somewhat the Cox-Merz relation, saying that if you have one material function in, say, G star in this case, this is correlated to another material function. This would be the loss tangent, but I don't know the correlation to do this directly. One more important relation to mention here is the so-called Cox-Merz relation, where the dynamic viscosity versus frequency is measured in this fashion here, 0 shear viscosity level, and then at high frequency. It's not shear thinning, but the value goes down. And this function plotted is, and compared to the steady shear viscosity, has exactly the same format. So if you have this relation from your experiment, you can change here this by putting the shear viscosity, and this one you replace with log shear rate, and then you would have exactly the same plot. And another relation which requires a linear viscoelastic experiment would be Gleissle's mirror relation. He looked at the startup of shear flow at constant rate. So the shear rate would be 0, and then it would be jumped to a constant value, and then kept constant here on, and the stress is growing, and reaching steady state, reaching a constant value. And the constant value of the stress divided by the shear rate would be the 0 shear viscosity. So this level is equal to the shear viscosity. But he found that this entire shape of the curve is identical to the shape of the viscosity curve if you flip it over. If you take this one and you just flip it over to the other side. I should have drawn it on the other side here. But if you flip it over, you get exactly this curve here. And you replace then T with 1 over gamma dot. And T replaced with 1 over gamma dot, and then you take the startup viscosity, and you get your steady shear viscosity. And this is your material function then in steady shear flow. This is all I wanted to talk about, the material functions, interrelation of material functions in linear viscoelasticity. The next step would be the measurement of material functions in specific experiments. So we will go to the experiments and to the analysis of the data, the conversion of dynamic mechanical data into the spectrum. In having the spectrum, then we can look at specific materials. We can look at blends, liquid crystal, and really expand and see what's the fingerprint of those materials. So that's the outlook. That's how we go forward. Thank you. Yes.